Good evening or afternoon, everyone. I hope that you guys are well. Depending on where you are in the world. So Prof had mentioned that he's running a bit late. So I think we have about 10 to 5 minutes of question and answers that we can get through. So if you guys have any questions that you want answered now, I think maybe this is your best time to go about with the questions. Of course, I think the capstone is the most important topic to touch on now, right? So I think for now we've went through about 9 weeks of content, right? And what we've essentially done is that we've prepared you and given you the skills that you could use, right? And what we now require of you now is to look for your own data sets, right? So you go look for a problem of your own and apply the very same skills that we've learned, that you have learned throughout the whole 10 weeks, right? So I think if we go to the week 9 of but maybe let me not go into too much detail into this because next week's session is mainly on this, right? But But we'll have a lengthy discussion, I think, next week where we're discussing the Capstone project. But just an overview of it is that you're looking for your own data. You are solving a problem um, using what is this? Using the set of skills that we've done, right? So sorry. So yeah, I think maybe that would answer Anya's question, right? And then I see she said whatever you're saying is about week 10, right? So yeah, this is the week 10 capstone project, right? For week 9 we haven't chosen a project to do for week 9, which is the explainable AI, because we haven't received the material for this week. I think we doubt that we might even give you any capstone project to submit for this. If we do, it probably would be a bonus. But because considering that we haven't published any material on this, I think it'd be very unfair to expect you to be submitting anything for this week, right? So you should be okay. I think maybe for now you could maybe put your energy towards the capstone project. Yes, does that answer your question? Okay, perfect. So don't stress too much about the weekly assignment. Those were just to make sure that you're on track. If you're struggling, we can pick up that someone is struggling here and there, right? But what is important is the capstone project that will be due, yes, on the 28th of July, right? So you probably have like about a month to get through this, right? Counting this week as well, right? So um do we select? No, you'll select your own capstone project, right? So this will be a project that you chose, and something that you are interested in, right? So so it'll just be marked by the mentors as well as the lecturers who are available. But this will be something that will be selected by you. Remember, you should also justify what it is that you're solving, how did you solve it, and have like a conclusion at the end of it, saying what model you used and your accuracy on the model, if you want to do the F1 accuracy, and what kind of errors are you getting, why are you getting those errors, and if maybe you want to print out your confusion matrix, that will also be a good way just to see how your model is also performing, right? So that is yeah. What capstone project uh, must the capstone project include all 9 weeks like machine learning? Yeah, of course. I think we'd love it for it to also include machine learning. In essence, it must be a machine learning project, right? So at least machine learning should be there. Um, yeah, I think it should include machine learning. Artificial intelligence, if your AI skills are at that level where you're able to also build an AI model, I think that would be really cool. But at least machine learning though. Using NumPy and Pandas visualization tools. Chris, it I think maybe it'd be wise to maybe to push yourself maybe and see how you're able to use the machine learning what you call this skills that you've learned. I think you have resources that you can go back and look at for the machine learning part of it, and then you should be fine. Daniel, oh yeah, you're in the room. Go ahead, Daniel.
Yeah, so I think I'm not sure why people still keep asking these questions all the time because we've specified the instruction in the capstone in the repo, link in the repo, which has been shared multiple times.
Yeah.
The capstone is fairly straightforward. Not every problem will require machine learning, right? Um, Machine learning is a case where you have enough data and you think you want to do classification. If you have some scientific research that you want to do, in astronomy, the first you need to think about is what kind of research do I want to do? And when you think about it, the next question is, does data exist? Right? Which is where you have to do, if you Google search, check for literature, search archives to see if you can find relevant data. And then if you find the relevant data, what we want to see is that is where you begin to now say,
Oke,
given the data that I
bentar Mas.
have, sorry,
Di
somebody's
mana
mic
ini?
is on.
Atas. Aku mau. Oke.
Not sure who's that. Yeah.
You can.
So yeah. So if you find the data, the next question is, given this data, what can I do with this data? Right? So we want to see the process of your problem. You want to see your research thinking method, justification in your problem. You state the problem you want to solve and justify why the data you want to use exists, the source of your data, how you query the data. Then when you collect data, you don't just completely do science with it. There are a few things that you have to do, quality checks, maybe do you have any kind of analysis that you want to do, right? That is what we want to see. For example, in one of the earlier lectures, Priya showed how to query Gaia data from a cluster, showing a particular portion of the sky, a cluster. Let's say, for example, we want to study maybe, say, main sequence stars in a cluster. You can go to archive and find a data, maybe Gaia data, it could be any other data. But then you need to do the filtering for the cluster. You need to query based on the region. We want to see how you do that. Then if you query data from the region, the next thing will now be, am I looking at main sequence stars? If you're looking at main sequence stars, then you have to begin to think of what are the criteria from Gaia that you can use to select main sequence stars. Are you looking at old stars, dead stars like white dwarfs? You can say, what are the criteria for me to select this? So we want to see the filtering. We want to see the, quality checks. And then from there, what kind of analysis do you want to do? Do you want to show us the population sample? Are you looking at the distribution, how the distribution looks like? Do you want to do some statistical analysis? That is when you can now jump into doing your exploratory data analysis, things like visualization. Is there any some of astrophysical transformation that you want to do? For example, if you have the magnitude of a star, and then you have the extinction. Do you want to do extinction correction? Where do you get the data? These are the kind of things that I want to see you do. Do you want to calculate the absolute magnitude? There's a formula for it, which even you can go to Google, it's fairly easy to do. Can you write a script on how to do that with Python and do all of those transformations? And if you do the transformation, do you want to show us a visualization of the distribution of your sources? Are there other kind of plots that you want to do? Right? Because majority of papers are not machine learning. Machine learning is only a case whereby you have done enough observation and you want to do some classification, regression, anomaly detection, time series analysis. You can do that. But you need to at least take us through the basics of the fundamentals of what you want to do. If you are confident with machine learning, go ahead and do machine learning. If you are not confident with machine learning, you have some scientific things that you want to do, please go do that. What we want to see is that you can fairly use Python to do your analysis from querying data to doing filtering, to doing data cleaning, to doing visualization, and doing statistical analysis, doing a couple of plots, right? When you do that, you'll be able to now have something that you can describe. If you look at Jupyter Notebook that have been sent to you, they usually come fairly with a number of tests describing things, showing examples, showing figures, explaining them. We want to see you do that by yourself, right? So please, let's not overflog this. This instructions is fairly easy where to get data from and the kind of problem that you need to think. But nobody will probably nobody will recommend problems for you. You have to think about the kind of problems that you want to do, right? I'm not sure if I answered your questions. And talking about pandas, of course, you have been taught NumPy and pandas in this course. You should make use of them. You have been taught matplotlib. You have been taught seaborn. Use them to make plots. You have been taught scikit-learn. If your problem involves machine learning, if it can use scikit-learn, then use scikit-learn and do classification if you want to do machine learning, right? So, and yes, Jupyter Notebook. In your Jupyter Notebook, you need to put your code examples in Google Colab. Google Colab is free. All you need is a Google account, right? And you can use it for free. Write your codes, write your text. You learn to use beautiful, write your text in Markdown. It's fairly easy to do. You can even go to AI and ask Google AI chat to it can ask it. You can ask it, how do I format my text? It can format your text for you. Yeah. In the project, should you include every data analysis techniques we have learned? Not necessarily, no. It's just like, for example, you did your undergraduate course. While doing your undergraduate course in the university, you took 1,001 courses. But before your graduation, you did a project. Now that project is on a topic, and in that project, you did not use all the knowledge that you used during your courses from first year to final year. You did not use it for that, right? You had to pick the things that are relevant for the problem that you want to solve. So don't think like a researcher. Think about the problem, how easy you want to solve the problem. Do not go and overcomplicate things, right? It's something that you can explain tomorrow, something you can be proud to say, oh, this is how I was able to come up with an idea, and this is how I did it, and this is the kind of result that I achieved. You can maybe see if you can reproduce what is published in a paper. If there's any paper that you like, you can say, okay, let me use this opportunity to see if I can replicate what they did in this paper. It's something like that works. Okay. If you read a paper and you like it, you can, if you go to Archive, find a topic, you can search the data on Archive, search it anywhere. It could be, it may not be, it could be even data somewhere else. You can probably reach out to the author and say, oh, can I use your data? Or if they listed their data somewhere else, you can take it. You just need to tell us where your data source is coming from and attach the link. That's the only thing that is needed from you. I don't know if this explains it. I don't know if it explains it. I don't know. There's any other question? Is there any other question? You can't see any in the chat. Okay, I'm going to send the link again. If you go to the GitHub repo, you'll see the project link there. I'm going to send you the capstone link. Please, you can save it on your, copy the link and save somewhere, just so you don't. It's fairly simple. The instructions there are fairly simple on how you need to structure it, right? So you see the modeling and analysis. The reason why we said modeling and analysis is if you think you want to perform machine learning, you can do that. But if your problem does not require machine learning, you can skip it. But you can also, in the whole description, justify why you don't need to do machine learning. So you don't just put some code and send. You have to write about what you have done. We want to see how your learning journey is, what motivation, the steps you took to get to your final results, and then in your and all that. So you can also ask Google about capstone projects. Yeah. We're not providing an example, and this should be intuitive research. If you look at the link, you will see the grading rubric, right? In the grading rubric, you will see, if you see, please take your time to look at the notebook structure. It said modeling analysis, if applicable, right? If it's applicable to your case, then you do it. Yeah. No, you can ask within your colleagues. We're not going to give you any capstone ideas. Even while I was discussing earlier, I fairly just said something. You can ask colleagues around you. Think about what you like. Think about what uh, things that you like in astronomy. You've been hearing about astronomy. I know some of you might probably be like undergraduate students, or maybe you do not have research experience. But just think about some of the things that you like. It could be exoplanets, it could be stars, it could be galaxies, it could be AGN, it could be you know, asteroids, small body systems, could be any kind of data, any kind of thing that you think. This morning, Ronaldo was talking about stellar flares, sun flares. It could be data on it. I want to like maybe check historical data and see if you can model it and all that. Yeah. Mm.
Daniel, I think maybe let's save the rest of the questions about capstone to maybe next week or the following week.
Yeah,
And
so we can do that next
And
week.
next week,
So thank you,
thank you,
Ronaldo.
Ronaldo. Welcome. Hi, thank you very much. So I'm here, so we can start.
of course, Profi, please go ahead.
Okay, let's go because you have a lot of stuff for today, and I'm very happy to be here again. So let me. Okay. So first of all, I needed to share my screen. Okay. Yeah. Okay, can you see my slides? Yeah.
Yes, Prof, we can see your slides.
Okay, fine. So this afternoon we are going to the module 2, where we go to space physics and astronomy, but facing some challenges for artificial intelligence, deep learning, machine learning tools in astronomy, astrophysics. This morning, I explained you the concept of XAI, take into account a very important application in space physics, that is the space weather forecasting. So this afternoon, we go to XAI. I'm not sure if all the students that were this morning session are here. So I'm going to do a quick review, okay? Just to be sure. In this morning, we discussed the XAI in a broad perspective, from prediction to trustworthy decision make. We assume that we have input data like observations, measurements, some context and prior knowledge, even from reports, not only data, but you can also have a metadata here. And we go to AI models, okay, based on machine learning, deep learning solutions and architectures. And then we get some output. The simplest example is a time series prediction based on, for example, recurrent neural networks models, which I'm pretty sure you are familiar. So when you say XAI, we have, let's say, not only the black box as an explanation based on the model that we are trying to get prediction, from where we are trying to get some prediction. I mean, the variables, physical variables. But we are we can go further and also do some kind of interpretation. In this morning, we use a model to predict the auroral activity in ionosphere related to the dynamics from the sun, from the Solar Dynamic Observatory, where we have images, and we have also time series from the GOES satellite for X-ray irradiance. And from that, we go to the magnetosphere, where we have some modifications in the magnetic field, and it can be measured by magnetometers on the Earth in high latitudes. And from that, we can measure a time series for the index that we call SIM-H, okay? And also DST. I explained that. And then we go to the auroral activity time series. And in the explanation, we'd like to use XAI methods like SHAP and LIME that we described this morning to understand which variables in our physical prediction model are more important, are let's say positively influence in the result that was predicted. And that's what we call the first box in this XAI pipeline for explanation. The question here is, why did the model produce those results or this result? So here, for example, in the space weather, we can say after this analysis that the storm alert was issued mainly because the interplanetary magnetic field BZ was strongly southward and solar wind velocity increased, for example. But we can go further and we go to interpretation. And what does this result mean scientifically? So give the result of physical and domain context should be addressed. So we can ask for the physical meaning, scientific consistency, causal relationships, domain knowledge, and contextualization. An example of output from that is the model predicts a severe geomagnetic storm consistent with the arrival of a CME observed 48 hours early, for example. But if it's a critical application, and there is something that we didn't like in the result, or there is some suspicions about the performance of the output, we can go to auditability. And the question here is, how was the model built and why did it fail or succeed? Even for when it succeeds, we can do also auditability. So the focus here ensure transparency and traceability of the entire pipeline. So we are talking about the data provenance, pre-processing steps, train, validation, test split, cross-validation strategy, hyperparameter search if you use only empirical criteria, or some optimization framework like Optuna. And also we need to open the box for the model architecture for any deep learning or machine learning architecture, and the versioning and the reproducibility. So we go from the raw data, pre-processing, training, validation, test, and deployment. And the output here, in the sense of XAI, will be the poor performance was caused by inadequate train test split and the insufficient representation of extreme events, for example, or bad data quality or something like that. And if in the critical application, there is some decision making that it was not a good one, there is some responsibility to use those results, we can go to accountability. So who is responsible for the consequence of this prediction? Fox define responsibility and consider the impact of decisions. So we are talking about operational impact, decision support, risk assessment, governance, human oversight, and responsibility chain. So the output is a false negative prediction prevented operators from protecting satellite systems, for example, in the space weather segment. So someone in the morning asked me, How we do that? We have tools to do auditability and accountability. No, actually not. We are in the state of art now, is working in this box, a little bit in this box, but we don't have too much on both here, 3 and 4. So that's a open house for young students, bring some solutions, some ideas, how to perform auditability and accountability in the XAI pipeline. Okay. So this year we have this 40 World Conference on Explainable Artificial Intelligence in Brazil. You'll be here next week. I'll be there to present this work. Okay. The explainable AI for operational space weather forecasting, an interpretable prototype for the Embrace INPE monitoring network. Embrace, as I told you this morning, is a service, not a lab for research. So we are now improving XAI in the whole pipeline of this service. And Mariana Rubetti is one of the co-authors, and she's here to show you hands-on today in the Google Colab, but not based on this application, but for astronomy. Separation using XAI to separate stars from galaxies. Okay. So this morning I show you that we have this model 1 for time series from GOES. It goes to CMH for magnetometers and ionosphere for auroral electron jet that also are measuring on Earth, on the ground. And of course, you can go for model 1 before the X-ray measurement that comes from spatial temporal data from the Solar Dynamic Observatory. Okay, so we discussed this in this morning. I'm not going to say not too much more about that. But what I want to discuss here, this is a quick review of this morning, is all those systems are very complex, okay? Involving plasma, and even in tokamaks, disruptions in plasma are a big challenge nowadays. We are trying to predict it, and for in a real time, in order to stabilize the magnetic field to keep the plasma stable, and then we can get like, let's say, 100 megawatts during 1 hour, so it to be very useful for our transition use of energy in the next 3 or 4 decades. Okay, so what we have here is a model that from one XAI tool that we call LIME, we saw also in this morning. We can get images from the sun, from Solar Dynamic Observatory, and calculate and get what we call hyperpixel from those images. Those hyperpixel have many applications. Applications related to understand how much of a such image could be more a fake one, like performed from a generative AI, or you can use also from a real data to localize the most important areas of pixels that are responsible for extreme fluctuations that are getting from the image. So we can get this that we call hyperpixel images, and you can use that for as an initial condition for some multiplicative cascade models that are very common in the field of plasma physics when you have spatial temporal dynamics. So using some LSTM, long short-term memory tools, we can try to predict the maximum areas based on hyperpixel concept, coming from some models based on multiplicative cascades. So that's just to show one simulation. So we have this, the initial condition is a hyperpixel of a plasma distribution in 2D. The model is a multiplicative cascade, and then we take all the average of maximums for each hyperpixel area, and you see how it goes in time, and it can be used for forecasting before we got extreme fluctuation. Okay, so but let's go to the time series from the solar physics, the most important one. The reason why the sun is so complex is the dynamo model, where we have the magnetic polar field turns in a toroidal one in a magnetic cycle that takes almost 11 years approximately. So we can see those measurements, and we can use, for example, recurrent neural networks to predict the maximum. And of course, we needed to come here and ask for XAI application of those predictions. Okay. So what we are going to, it was a quick review of what we did in this morning, okay? And then we go to our lecture of this module 2. The contents for today are, the first one, I would also to show you a late hands-on tool for time series analysis. It was almost 1 month ago, we did this lecture, okay? I'm showing you, I'm sending you this link as a homework. You are going to do that in the next days, next weeks, and I'll be open to receive your back information about this use. And so I'm going to show you light curve from variable stars, okay, canonical variable one that are real. So here, people, there is no XAI in this notebook, okay, 0 XAI. But what you can do is to bring some XAI solutions after this lecture to this notebook. This notebook is related to the module 1, time series analysis in astronomy. And okay, then we go to XAI for galaxy morphological classification, just some concepts. And then the third activity for today, for this afternoon, will be XAI for star-galaxy separation or classification. That's a hands-on with Mariana Hubert. Okay, let me just show you what I'm going to send you for the homework. The homework is this time series analysis that's for variable stars. So we are going to get this notebook, okay? The idea is to see this zooming this time series. This is a light curve for a variable star. And then we can construct this phase dispersion to get the periods of this variable star, the regular, almost quasi-regular periodic fluctuations. That's a very important one to understand the underlying physics for this kind of process. Okay, so let's come back here. So morphology. Let's talk about morphology. In morphology, we have we can go for a more technical structural interpretation. The more important separation is between elliptical and spiral structures, galaxies. Of course, some structures are related also more physical and environmental approaches. And then we can go to early type versus late type. Okay, and we have this pretoria of objects, and we should be able to classify different patterns that usually are defined by the Hubble fork classification. We have here the elliptical ones, the spiral ones, barred spiral, many subtypes, and also irregular ones. So there are a plethora of different patterns, but there is this dichotomy that we call elliptical versus spiral. That's very important because for cosmology, for example, we need to classify billions of objects in order to give it to the cosmologists a lot of elliptical objects, for example, or early type objects. That's a very important approach for cosmology. That's why we do a very hard work trying to classify morphologically different kinds of galaxies. Okay, as a reference for you, we have been working on this pattern analysis for the last 10 years. We publish some papers that I recommend for to get more expertise in the subject. So we have this gradient pattern analysis applied to galaxy morphology. I'm going to talk a little bit about this technique. That's a very important one. Then we have the machine and deep learning applied to galaxy morphology in a comparative study. And then this is for, we classify around the 55,000 objects for slow and digital sky survey. Data release 7, based on Galaxy Zoo 1 catalog. So it has been a supervised machine learning application, okay, based on the Galaxy Zoo pre-classification. And here we use a hybrid approach, bringing also unsupervised autoencoder and transformers applications. And for that, we got a greater sample around 670,000 objects, and also including some physical analysis of T-type value. So we do this kind of classification based on two different systems. The CAS, that the CAS is for concentration, symmetry, smoothness, that they were calculated on the images, and also entropy, Gini, and gradient pattern analysis. And so we compare all those descriptors, trying to get the best pair of descriptors to use in a parameter spacer like that. Which one are the best pair in order to classify billions of galaxies in an agile way with a very low level of bias. So, of course, for each one of them, we see some can separate it very well, elliptical from spiral, also trying to understand the T-type models, and there are many, many different approaches for that. So I'm going to show you only some final results. But the systems for morphometrics analysis, the most common one is this one, the CAS. It has been used for more than 30 years in the galaxy classification, and it's based on the concentration, using the Petrosian radius for the brightness of the object. It's being 80% of the brightness, 20% of the brightness, so we do this ratio. And this is a very useful to classify elliptical ones. It maximizes for elliptical objects. We have also asymmetry based on the rotation of the image. So we can do this rotating the image and subtracting from the background, the initial background. So this is very, very useful, and it maximizes for elliptical morphology. Also, we have the smoothness. It's almost actually it's the same formula, but instead to have the amplitude for a rotated image, we have the smoothed. We are smoothing the image, and we do the same calculation. This is very interesting, and also this maximizes the features that are localized in the image. It means that it maximizes too for spirals. On the right, we have the AGG system. The E is for entropy. We have this calculation for the entropy of the amplitudes here, the intensities in the image. It also maximizes for spirals. When it's very, very homogeneous, we have a very low entropy, and here a very high entropy, sorry. And we have a Gini. Gini is also for homogeneity. It comes from the social sciences, when we have coming money very well distributed among people. The homogeneity is very high, so G is very low. Okay, total homogeneity G is very low, and the total inhomogeneity G is almost 1. This is very good because it's a normalized matrix, and it has been a very good descriptors for to distinguish elliptical from spirals. So G2 is a quite new matrix. It comes from gradient pattern ads from our group. We introduced that 20 years ago. It has been applied for many pattern recognition in different fields. And in Galaxy, we applied this formula. This is easy to understand because instead to analyze the value from each pixel of the image, the amplitudes, I can say, we analyze the gradient field from the image. So I calculated the x, dy for each amplitude, or for each pixel, and we get this new domain that we call gradient domain. In the gradient domain, we can measure it, we can extract metrics from the diversity of modules and the diversity of phases in this gradient field. And we can compose many different descriptors. This descriptor G2 is based on the ratio between all the asymmetric vectors by the total vectors. What are symmetric ones? Asymmetric ones are the vectors that has been removed after a comparison for bilateral symmetry. So we have the vertical and horizontal axis, and we compare vector. For example, if I have a Gaussian here, all the vectors will be removed. Okay, of course, spiral is a very high asymmetric one in terms of bilateral asymmetry. You see, this arm is here. If I take the vertical axis here, is here, and the other one is around here. So there is no bilateral symmetry in the vertical axis. As for the human face, for example, we have a bilateral symmetry in the vertical axis. We have one eye on the right, another eye on the left, and this is a kind of a bilateral symmetry, very easy to understand. And in this formula, confluence is this ratio among all the summation of asymmetric vectors. And here without the module and here with the module. What means that? It means that when you have a kind of a planar flow, a laminar flow, it goes to 0.5. When you have a totally disordered asymmetric one, we go to 1. And when you have a totally symmetric one, we go to 0. And we can get others gradient moments also from this gradient pattern analysis. So we have here at least 6 metrics, or let's say, we can say also descriptors for each one of those metrics. So gradient pattern analysis, as I told you, is a computational operator. Okay, it's not a statistical one. It's like a fingerprint of the pattern for a given size. So when I have a Gaussian one, it goes to 0. GA is for the 4 gradient moments, one for triangulation like that, for asymmetric vectors. For example, for a spiral, this is for elliptical, and the confluence is very high here. We remove almost all the pairs of vectors here for a given tolerance. It means they have the same module, but they have opposite phase in a given tolerance. So we start to removing all the symmetric vectors, so at the final it to be 0. Like a Gaussian or Besselian 2D function, we get to 0 as well. So here we have an example where those values are not 0. So we can count all the asymmetric vectors here, put this VA, took the original size of the image here, we have these vectors, and we compute this ratio for the confluence. Then we can see that we will have more confluence here, so less vectors here, and that's why a GPA is able to distinguish those kind of patterns. I can apply that even in the RGB original image. I can apply that also on the grayscale. I can apply also that in the binary one. Doesn't matter. Okay, it depends on the comparison framework that I'm defining at the beginning. In the beginning. So gradient pattern analysis has just to be clear, we apply that in the elementary matrix. This is 3 by 3 matrix, just to get the simplest one, and then we get the gradient field. Gradient field has been separated in 2 matrices, one for the modules, another one for the phases, and I can compose also a hybrid number here, like an entropy or a complex number, bringing together module and phases. So I can define many metrics here. So take a look in this paper for the details about GPA. Okay, you can use the GPA for many applications, not only in astronomy or galaxy morphology, but for any pattern analysis outside of the simplest framework based on statistical moments, for example. So just another example. So G2 goes to 0 when I have a total bilateral symmetry. It goes to 0.5 when it's a laminar flow, and it goes to 1 when we have all vectors based on module and phases are different each other. So that's the idea. So we have using that in order to degrade images using this machine learning approach, deep learning approach. We use a cycle again and the peaks to peaks to degrade images from a given telescope to another. So if I have an image from James Webb Telescope, I can degrade that as a Sloan Digital Sky Survey image in the same level. Then I can use the same classifier based only on the idea of a hyperpixel. In this case, the gradient of asymmetry works also like a line technique. This is a kind of hyperpixel representation from the gradient domain. So it's a minimal information that keeps the structure very coherent. So I can say this is a typical bar spiral, this is a typical more irregular galaxy, and this is a typical polar ring one. This image comes from the Sloan Digital Sky Survey. This image comes from Hubble Space Telescope, and this image comes from James Webb Telescope. All of them, after passing through this degrading deep learning architecture, takes the same as we get in the Sloan Digital Sky Survey. So I can apply GPA on that and use this gradient representation to classify in a very agile, quickly way billions of objects. Okay, so why that? How can generative AI positively impact the morphological classification of galaxies? Okay, so here we are discussing the role of generative AI in training a hyper citizen boat for galaxy zoo-like environment. So we are talking about a citizen boat for galaxy. This is the same way we have in the galaxy zoo. People go to the system, go to the platform. It doesn't matter if it's an astronomer or not. So this guy is going there to help to take faster a classification of many objects. So we are bringing the boat for that, and the boat is based on the degradation of images coming from any telescope and comparing with an image as it has been given by Sloan Digital Sky Survey. Why Sloan Digital Sky Survey? Because for Sloan, we already have this parameter space where we can get the best both metrics here, for example, G2 and smoothness, and we can separate it quite well, elliptical and spiral. We see that the separation is not 100%. We have some intersection overlapping among those types. And this overlapping has many reasons. One of the reasons is, for example, the inclination of the object, if it's not a face on or edge on. So there is some limitation for the inclination and the other beyond other problems. But that's a very good classification. So when we get the image from James Webb, for example, for polar ring, we put that in the same level of Sloan digital sky survey that is responsible for this background with thousands of galaxies pre-classified, and we see that the polar ring, the cartwheel galaxy, is in this point. So it's a new sector for a galaxy that is outside of the dichotomy, elliptical spiral dichotomy. Okay, so we call that SciMorph 2DX platform. We have been working a lot on that, and we have a new version for this one. So, but generative AI, why you need XAI in this kind of application? Because of course, the grading image it's okay. I'm the grading image. It means that I can apply sharp analysis here, and I can show that all the pixels that belongs to this hyperpixel representation from the gradient domain, they are very positive to classify this galaxy as a Sloan digital sky survey object. But if I start to improve the image using generative AI, for example, give him the time evolution of this polar ring galaxy. So I can train a lexical with many informations for this lexical, like a number of galaxies, snapshots for stamps, many stamps, elliptical examples, spiral examples, lenticular examples, ring examples, etc., early type, and many informations. He can construct a reasonable evolution for polar ring. Okay, but I mean, this is a not a good one to do classification, morphological, comparing to other data from other telescopes. And the SHAP can tell us that is not good because it's saying the red one here is saying that this hyperpixel representation is a bad one to compare with Sloan digital sky survey. Okay, so this is a very important application of LIME SHAP applications, bring it in the framework of a galaxy morphological analysis. Okay, so for LSST, we are going to face billions of galaxies, 20 billions of galaxies in this range of AB magnitude. Okay, so we are expecting from 35 billion objects that at least 20 billions will be galaxies. And it means that we are going to do an acquisition of almost 12 terabytes data per night. So we have data cubes of galaxies, and it's going to increase it a long time and for different data releasing. And the idea here is to be agile. So that's the first deep field from LSST. We have the Virgo cluster finder chart. This has been annotated, so we have all the objects here. This is from Vera Rubin Observatory, beautiful survey. And what we do here, just to test our new version of SciMorph 2DX, we choose a stamp here, okay, where we see very well a spiral object, and we go there, and we took this stamp. We see both are spiral here. And let me show you just the classification of one of those objects, this one. And then when you go to the SciMorph 2DX, the new version platform, we see the object here. We have also the stamp histogram for this object. We got the pre-processing cleaning for the grayscale using the hyperpixel based on the gradient field and also Delaunay triangulation. And then we improve this image. Okay, so we have a very, very good features. We have this cleanup image from that one, and then we need to apply the deep learning pixel to pixel to degrade this image as slow digital sky survey object, and then we get it. Then we are able to classify that in our 2D space parameter. So we do the gradient pattern analysis again. Okay, we extract the symmetric vectors. We have here only the asymmetrical one, and it goes to be classified as a spiral one here in this point in the classification. So that's a very interesting tool that is available, will be available to the community. The releasing of that tool will be November 26th this year. Okay, and this is related to the Brazilian participation group. So that's a very important tool for our BRICS astronomy community. This is from Brazilian in the LSST framework. We have also cooperation with Chinese people here, and starting some collaborations also with people from South Africa. Okay, so let's go to SHAP that I explained this morning. So we have here, again, I'm showing you the metrics. And when you apply the SHAP for that, we are applying what means SHAP for the people that were not in this morning in the lecture. Shapley means Shapley additive explanations. Okay, it comes from the game theory. Game theory you can divide it in competitive games and also competitive plus cooperative games. Of course, every game are competitive, and but there are games that we can collaborate in a subset of players in order to get very good results at the final of the game. So if I have people playing like a soccer team, or if you have people playing cards in different groups, we have a kind of synergetics approach. We have some cooperation involved in that. When you have cooperation, we have what we call coalition. For each step of the game, we have some coalition. People are trying to change information. Doesn't matter which type of information, doesn't matter what quality is coming from this information, but it means there are some coalition. People are trying to cooperate in order to get the output that we know. Okay, so Sharpie is a XAI application, so we need to have the output to apply that. Once you have the output, we go to this formula, and we can apply. I explained this morning this formula in detail. I'm not going to do that now, but just to have a look here, this formula means I have a probability. What's the probability to get a polar ring considering a given descriptor? As I told you, we have a couple of the descriptors. 6 I showed in the last slide, but we can also bring the other descriptor. Here I choose 8 descriptors. Okay, 2 from gradient pattern analysis, G1 and G2. G1 is based on the modules of the gradient field, G2 based on the phases. G is the Gini, E is for entropy, Cas is concentration, symmetry, smoothness, and also I brought to this analysis the 4 statistical moments: the mean, the variance, the asymmetry, and the kurtosis. Okay, so when I put all those descriptors in the game, it means each one is one of these phi here. Okay, I do the summation, making some comparisons of the values that classify spirals and ellipticals. So each comparison is a coalition. So I have 1,000 millions of combinations, because it's a factorial here, and I have many subsets of collisions to compare with the function of each S in each step. So the probability per ring for a given descriptor will be calculated like that, okay? This is activation function. I can use many here. Here I'm using the Gaussian arrow, linear Gaussian arrow here. And when I apply that, I can get sharp output for galaxy morphology. So here are all the features, and I can say that the G2 and the entropy, and maybe I can bring also G1 and G, are the most positive ones in order to discriminate spiral from elliptical, and also, of course, the cartwheel that's outside of this dichotomy. So I'm using this result is for polar ring. So it means that these features are very have a very good performance in order to classify regular galaxies and very special patterns like a polar ring. And that's very interesting to see here that the statistical traditional moments are not able. Sometimes they are very confusing about this kind of classification. They cannot separate, for example, the mean, the variance and mean could be the same for the three classes that we are comparing: elliptical, spiral, and polar ring. Okay, so they are not very good to this. So I'm opening the box of that machine learning application, applying this sharply additive explanation for comparing all the features or the descriptors based on the pattern features of those classes. Okay. So that's very important. But we can go beyond the simple classification and we can apply GPA for gradient pattern analysis of more complex structures. So to do that, we need a high level segmentation pipeline. So when I want to know exactly if I can classify that as a merging pattern, a pre-merging, ongoing merging, or after merging dynamics. So for do that, I need segmentation, very high level of segmentation. Okay, and I know that Simorph 2D is very good for that, but we are improving the segmentation here to apply the GPA. So we do the segmentation and we go to the mosaic output, and that's interesting result because those three that has like a more asymmetrical distribution, like 0.45, they are in the same redshift. They are in the same system. This one is not in the same system. It's in redshift 0.77. So here we have 0.39 as the average of this gradient field. So this is one example. I recommend you to read this paper. That's a very recent one. We published that this month. And here we explain in a very good detail all the pipeline for the how we segmented the image, how we do the pre-processing before we go to this kind of gradient pattern analysis. Actually, here we don't have a gradient pattern analysis. We have only the segmentation, and there will be a second paper where we are bringing the analytical tools. So what we are going to do now, we go to the hands-on. In this hands-on, we are going to apply SHAP for star-galaxy separation. The notebook that Mariana has been prepared is able to investigate the characteristics of all the objects detected in the dark energy survey. That's an imaging survey conducted with the dark energy camera, the CAN, that are on this 4-meter Blanco telescope. We can see the Blanco telescope, Victor Blanco telescope here. This is located in Serra Tololo in Chile. There are coordinates here, the diameter, exactly one collecting area, and this is the location. some pictures from this telescope and observatory. And the first data release, of course, is a complex one, and we can go to the magnitude domain. Magnitude domain comprises about 400 million stars, galaxies, and quasars. And so the first big challenge is to separate stars from galaxies. So Mariana is going to show you how to perform that based on some machine learning applications, bringing the sharp approach to this separation. So here we see a separation of the galaxies here, a good one, and stars here. Okay, a bad one here for galaxies, a bad one here for stars. That's the output from SHAP. Explain us that the squid model will be the most positive one to this kind of separation. So Mariana, I bring you to the stage. So Molebo, can you do you are in the floor now to do this, and I will say thank you. And as we are in the World Cup season, I put this extra hands-on for you. Run the numbers, and I ask you, it's possible for these two stars to meet in the grand final? I vote in the BRICS guy, okay? I hope you are coming with me. Thank you very much, people, and let's go to the hands-on. If you have any questions, or let's say if you have some comment, if not, Mariana, please come to the stage.
Okay, so can I share my screen now?
Oh, just I'm stopping sharing. Yeah, okay.
Let me share. Just a minute.
Yeah, take your time.
So what are you seeing? My screen?
Yes.
Okay. Let me put this. Okay, so you are seeing my screen, right? Just confirm, please, because I'm not seeing that. Okay, thank you. So I give you the hands-on on astrophysics. And what I prepared is I prepared a notebook that we will train a machine learning model that is a random forest model for classifying stars and galaxies. And then we will apply the explainable tools of the SHAP library for us to understand how the model is making the classifications. So let's begin with this. We should do a pip install of Astro Data Lab that we will need for this notebook. And here is the cam, dark energy camera. So we use images of the data from the dark energy camera from the filter G, R, I, and Z. So this is an image of the cam, and we can see that the objects are all mixed, of course. We have stars from our own galaxy. We have other distant galaxies at distant redshifts, and we also have another class of objects that are called quasars. And these objects, they hold supermassive black holes, and they are accreting star and emitting radiation. But in this notebook, we will focus on classifying stars and galaxies. And I will show you how we can do this. So we use in our model for classifying these objects, we use magnitudes and colors. I guess you're all already familiar with magnitudes that are calculated based on the luminosity of the sources. And the colors are the difference between different magnitudes. So we have this G minus R, R minus Z. These are examples of colors, and we'll use this in our machine learning models. We also use object shapes, and this is this spread model. This is basically quantifies how much an object is extended. So for a spread model of 0, it is a point-like source. And if spread model is bigger than 0.003, then you begin to have extended sources. We also use the object types that is described by this class star parameter. This is calculated by extractor, and it gives us a value range from 0 if it's a galaxy-like, it's not a point-like source, to 1 for a stellar-like or a point-like source. And we also use also the signal to noise ratio. So here is how we can query the data from the desk photometric catalog. We can do this in the SQL. So this is the structure of the query. We can select, then you put the magnitudes we use. So it's magnitude on the G band, the magnitude in the R, and the magnitude on Z, and also that spread model. We are also want the class star, the signal to noise, and also we're adding here the position of the in space, so radiation and declination. So we're selecting these attributes from the catalog. This is the catalog. This is another condition that is requiring the error to be greater than 0 to be positive errors. It's not crucial for analysis, but it's a good practice. We will order these objects by their identity, and we will limit them to 300,000 objects for this query. So this is how we get the data. We can run this client query, and we can run this like this, and convert this in a pandas data frame. And we can assign then not a number values for infinity or minus infinity. Then we can filter some invalid magnitudes. These magnitudes greater than 90 are mostly errors. So we're just getting rid of this kind of objects that are with invalid magnitudes. So we are filtering our data for magnitudes with values less than 90. And also we make a signal to noise cut, since we want to get rid of noisy objects. This will improve the performance of our machine learning model. We also can filter by the spread model, because it should be inside this range of values from -1 to 1. So we would just select objects with this valid spread model values. So after cleaning our sample, we recover 1/3 of the original sample. And we can take a look at our data frame. If you put the head, and then you can see the first lines of the data frame with the column names and the objects. So if you put the columns, then you can see the names of the columns and check if everything we need is here. So now we can build a color diagram. Just as I told you, we can define a color as a difference between magnitudes. So here we are building the color indexes, and we can plot these objects that we selected from the DCAN in this color magnitude diagram. So we can see that the objects are pretty mixed. We can see that different trends, that there is 2 trends overlapping here. There is this one here, and there is this other one. And there's also this diffuse cloud more spread over the diagram. So in these objects, we have stars, we have galaxies, and we also have quasars. But we can disentangle this with the help of the class star parameter that we got from Sextacto. So this, I will show you how we can do this. So let's define good galaxies as objects with class star with less than 0.5 in all bands. Good stars, objects with class star greater than 0.5 in all bands. And the other ones that are bad galaxies and bad stars, they are bad galaxies, that they are just like the galaxies. They are defined as with class star less than 0.5, but in the other bands, it might have greater than this value. And the bad stars are the objects with class star greater than 0.5, but in the other bands, they may have a value lower than that. So with these definitions, we can, here is just a code for the color diagram. This is how we're going to filter the data frame. So here is the good galaxies, and just the definition that I told you, that are class star less than 0.5 for all the filters. And here the good stars and not good galaxies and not good stars. And then you can see how it looks like in the diagram. And we could actually disentangle the tendencies. So here we can separate this tendency for good galaxies and this tendency for good stars. We can also take a look at how bad galaxies and bad stars are behaving. And you can see that let me see here. Okay. So we can see that bad galaxies resembles the good stars, right? So these bad galaxies and bad stars, they are like mixed objects. And so we will just remain in this notebook. We will just remain with good galaxies and good stars so that we can train our machine learning model and go ahead for the explainability of our model. So we will assume that good galaxies are in fact galaxies and that good stars are in fact stars, just for this notebook. So this is how we're gonna train our model. So we will use a random forest model. We will use as an input the color and the morphology characteristics of the objects into this model that is a random forest, and then the model will give us a classification of a star or a galaxy. So very interesting questions, as important questions, scientific questions are: which features are most important for the predictions? Or how does a given feature affect the prediction? Or even we can look at individual predictions, like if you're interested in how a model predicted a star for a specific object, then the explainable tools will help us understand why the model is classifying objects as stars or galaxies. So let's go to the model first. Here we use a random forest. And random forest, they basically work with random trees. So in these trees, in the nodes of the trees, the model have to make decisions based on the features. Like if you have a R minus I color of 0.5, and if you have a greater than 0.5, you go this way. And if you have less than 0.5, you should go to the other way. So in the nodes, you have to make decisions based on the features. And for the random forest, the features are randomly selected. So the trees are all different from each other. And also the sample used for training the trees, they are also different because they are subsample. They are sampled with replacement. So they are all different trees. And at the end of the trees, you get the classification for each object. So the final classification for the random forest is the majority of the votes in the case of this star galaxy classification. So if the tree 1 classified as star and the tree 2 as star and the third tree classified as a galaxy, then the majority will be star. The object will be classified as a star. So this is how it works. And here is the model. So this is the data for the model. We are concatenating just the good galaxies and the good stars. we also make here a new variable named is star based on our definitions of what is a star and what is a galaxy that I presented you based on this class star parameter. So this is the new variable. And we have the features. These are the features that the colors that will enter the model. And also this spread model that is how it accounts for how extended is the source. So the features are entering the model. And y will be the new variable that we just defined that is a galaxy or is a star. So this is how we split into training and testables. We want test size of 0.2. It's 20% of the sample will be for test. And here is the model. This is we're designating the model here. This is a random forest classifier. I put this 300 trees for this forest. Here is the fit of the model. You can put the train data here to train your model. And then it does when you put the model does the prediction it predicts. So this is the classification report of our model. So the accuracy was very high. It's like 97%. It's expected to be a very high score because we're just keeping the easy objects of the classifications, like the good galaxies and good stars. Those ones that are difficult to classify, we just excluded for the sample. So that's why it's giving us a very good result. We also see that we have much more galaxies than stars. So we have like 1,300 galaxies and 13,000 galaxies and 2,000 stars. And so the model, it learned more to identify a galaxy because of the number of the galaxies really greater than the number of the stars. So it works better for identifying, classifying as galaxies than for stars. So here is, you can just visualize the decision trees. You can put this number of trees here. You can also change this if you want to see more trees, just to have an idea what's happening. And Reinaldo already explained us about the Shapley. So the Shap values, they represent the contribution of each feature in relation to the average prediction for the whole data set. So the absolute value of the Shap value, it gives us the importance of that feature for the prediction. And the signal of the Shap value, for example, if we want the Shap values for the classification of star, if we have positive Shap values, then it implies that it is increasing the prediction for star, and negative Shap values, it's decreasing the prediction for star. So we can extract I will show you how we can extract the Shap values. This is a tree explainer. This works well for random forests. And here we can extract the Shap values with the explainer. So you put explainer dot Shap values for the sample. You want to extract the Shap values, and then we can make the plots. So we have the summary plot. That is this. It gives us an idea of the global impact of the feature on the model. So here we can see that this is in the x-axis, we can see the mean of the absolute Shap value. So it is ordered by the importance of for the predictions of the model. So the spread model is it shows the greater influence for the predictions, followed by the colors. Here, how you can create this, you put dot summary plot. And if you put 1 here, you are selecting star. If you put 0, you will be selecting galaxy. There's something in my presentation. The blue one is. Oh, let me see the other plot here. This is the bee swarm plot. The bee swarm plot is a little different from this one because it is not a mean absolute value of shape value. It has the actual shape value. So for each object. So that's why you can see dots here. It's not a mean value. It's a shape value for each object. So you can see the features here. And it's also ordered by the importance of the feature for the classification. So we have the spread that gives us how much extended the source is, and the colors. When you have negative shape values, it means that it is pulling the predictions away from the star classification, because here we want shape values for stars. So when you have positive shape values, it will be pulling the predictions towards a star. And if you have negative shape values, it will be pulling the predictions towards a galaxy. So we can see that this colored bar here, it shows the features values. So for the spread model, this pink dots, it is the high values of the spread model. And you can see that these high values, they are very concentrated on negative shape values. And this means that this high spread model is pulling the predictions towards galaxy. And the low value of spread model, that means that the source are more compact. They are pushing the predictions for, they have positive shape values, so they are pulling the predictions for the star classification. So the spread model is quite clear, the influence on the classification, but the colors, they are mixed. We saw on the color diagram that these stars and galaxies, they occupy many times they occupy the same region of the color diagram, so they're not so reliable for this classification. Here, this is another kind of shape plot. That is when you have a classification and you want to see what happened to that prediction. You want to see, well, why an object was classified as a star or a galaxy. So this is the waterfall plot. And here in this code, we are selecting a misclassified object. Here you can also change this number to select other misclassified objects to check what's happened to do this misclassification. And here is how you generate the waterfall plot. So it puts shape plots waterfall, and you have to put this shape explanation here that you generated here in this line. So this is the waterfall plot, and this is for a single prediction. So this object was classified as a galaxy, but it is actually a star. So what happens here is this value is the average prediction for the whole data set. So it's like 15% of the objects are classified as stars. And these gives us the shape values for each feature. So in Reinaldo's presentation, the blue was when shape values were positives. And here the colors are just changed, but we can understand this as well. So Here, the reds are pushing the model towards classification for star, and the blue is pulling the model for classification as galaxy. So here, this is the average of the predictions, and these are the influence of the colors. So for this object, this feature had the greater importance than the spread model, and that's why it's here in the first place, and then it's followed by the spread model, and then by the other colors. So this feature, this color, this is the value of the color. So these are the values of the features, and these here inside the bar are the shape values. So this feature, it contributed to the model for the classification as a galaxy, not a star. And so this feature, the spread model, contributed to the galaxy classification. And just this color contributed to the star classification. So the combination of these features um, resulted in the galaxy classification. So here, this is just an explanation if you want to take a read at home and for your own. And this is the violin plot. So I was just curious because this value of the spread model is minus 0.04, and I wanted to compare for the shape values for the objects that were correctly classified as stars, and I want to compare to see if it's less or if it's the same. And what we see with the violin plot here with the shape values is that for the correctly classified objects as stars, the shape values for the spread model are like more than 0.6. So they have a great importance on the classification. And this did not occur with our misclassified object, that it was like minus 0.004. So it was a very low shape value, meaning that it was not very important for our classification. This is if you want to take a look at the distribution of shape values for this spread model. It's just like the violin graph, okay? It's just the count and the shape value for the correctly classified stars. And I was just wanted to check in more detail what was the difference between this shape value for the misclassified objects, that is this vertical line, and for the correctly classified stars. And we see that there is a big difference. If you wanted to see, instead of the shape value, you could also look for the directive for the value of the feature, just not for the shape value of the feature, but the value of the feature, the real value of the feature. You could also plot an histogram to see. And the spread model for this object that was misclassified as a galaxy, it has a quite big spread model value compared to the correctly classified stars. So let's go to another shape force plot. This force plot it resembles the waterfall plot, since it gives us this is the probability of prediction of a source being in a star or a galaxy. There's something that I forgot to tell you. Let me come back there to show you something. This is the overall prediction of the model for being a star. So if it's greater than 0.5, it is classified as a star. If it's less than 0.5, it's classified as a galaxy. So this is the average, and then when you sum the contribution of the features, you see that the value of the probability of it being star is very low. So that's why it was classified as a galaxy. So let's come back to the force plot that is very like this one. So it also shows the probability of being classified as a star. That is a very low probability. And it also it puts from the left, it puts the features that contributed for classifying as star, and for the right, the features that contributed for classifying as galaxy. So this should be interactive. Maybe you can use this interactiveness in home. Here is not working, but you can pull the features. And something very interesting that you can pick this force plot, and you can stack them vertically, and then you get this very nice plot, and it is also interactive. And this is my favorite one. Here you see the probability of the model of predicting a star. And here you can, this is ordering, sampling by the order of the outputs value. So here comes the most probable stars, and then it's decreasing the probability of being a star. And there's something interesting that you see that seems like the spread model is shrinking when you have the lower confiability of being a star. That looks like the spread model is shrinking, and the colors are playing a role. And this is an interactive graph, so you can also change here the x axis. So you can put the original sample ordering, but then you get different insights, so you can choose. Also here you can look for different options here. This one is I think it's gives us the better view of what's happening. This one. But you can try at home and try different configurations. That is the sharp dependence plot. And this answer, how does a given feature influence the model prediction? So we have this, we have the Sharpe value for these features. We have the spread model, and then we have the Sharpe value for the spread model. We know that positive Sharpe values pulls the prediction toward stars, and the negative Sharpe values pulls predictions toward galaxies. So in this region, we have transition region for the classification, and this is what we call decision boundary. It might give us some physical intuition of what's happening with the model for it to predict as a galaxy or as a star. So it's for spread models. For the lower values for spread models, the model is predicting a star, and for the higher values of spread models, the model is predicting as galaxies, because it's negative, right? Positive for stars and negative for galaxies. And this is the final plot that I'm bringing here in this notebook. That is the decision plot. And then we are visualizing the prediction path of the objects. So it begins here in the expected value for the whole sample. So it's for classifying stars, it's 15%. So it's starting here at 15%. And it is summing the Sharpe values for the features. So this object, after the contribution of I minus Z, it comes here, and then it goes here and here. And it is also ordered with importance. So the spread model is the one that is most influencing the objects. And this is useful if you want to compare why some objects are classified in a similar way or in different way. What's happening with the classifications that may be deviating for some reason. So this is why we use this decision plot. So, okay, this is let me show you here. This is how you plot the decision plot, and then you put this explainer. And this is for stars. If you want for galaxies, then it's for, you should put 0. And so I will stop sharing, and you can make questions if you want. So let me hear. Okay, are you hearing me?
Hi, Mariana.
Okay, so if you have any doubts, you can ask me now.
So for students, if you have any comments or questions for me or Mariana, please come to stage. Molebo?
Yes, Prof.
Yeah.
There's one
Did you
question in
get
the
some questions in the chat or?
yes, there's one.
This
The
one,
first one
the first one.
is XAI useful for exoplanet detection?
Yes, it is useful for exoplanet detection. I guess it's useful for any kind of analysis you want to do with machine learning models. So if you're using machine learning model to detect planets, then it might be useful as well.
Perfect. And then I think let's deal with Kiran's question and then go to Shibam. Kiran's question: what criteria should be used to determine the optimal number of precision in estimations in a random forest model?
What is the question, please? I didn't understand.
So it's also in the chat. He's asking what criteria should they use to determine the optimal number of trees within your model. You know in your wanted, I think you had about 300 trees in your model. So how do you calculate? How do you get to the 300 number?
I guess Reinaldo maybe can explain this better than me. Reinaldo, do you want to explain this?
Yeah, the amount of how much is the tree is shallow or not depends on the amount of objects. For example, in that case, for each class that we are trying to use to distinguish among them. So for this one, a random forest is almost like the hidden layers that we use for deep learning here. So I'm thinking for this application, it comes from a tentative, right, Mariana? If there is an optimal one that I don't know how many branches that did you use in this random forest. If you if you
Yes, it was the default one.
Yeah, there is a default one, but this default one depends on the architecture of the random forest in terms of how many classes you are going to separate. So in that case, you are trying to separate two classes, but based on six values, right? Of how many
Yes,
colors.
three colors and the spread model, so 4 features.
So usually it goes like a factorial of this product. So we have a factorial of three. There will be trees. No, sorry, six. Okay, so that's the number that goes to the number of branches, and I think there are more than 10 branches in your random forest, maybe more, right?
Yes, yes, yes.
Yeah, maybe you can see in the algorithm this number. I'm not sure.
Okay. No,
This
perfect.
input in the algorithm.
Maybe let's take a hand and then we'll get back to Kiran's second question. I think, or maybe let's deal with Kiran's because it's a follow-up of the question he just asked now.
Oh yeah.
And he asked, how does increasing the number of trees in a random forest affect the interpretability of the sharp feature in contributing to the star galaxy classification? It's a mouthful.
Yeah, actually, I don't know the answer because, for the random forest, but because, SHAP, when I apply SHAP, this is proportional to the coalition number, the factorial of S. In that case, we have the branches are not exactly the descriptors, not the number of branches. Maybe I'm not sure. If it's, yeah, I need to take a look on that, Emolable. I'm not able to answer. I don't want to say to give a perhaps answer. So
It's okay, but since they also be getting the link to this GitHub, they can also play with the numbers and see how it affects their results. So I think it'd be good for them to also maybe have a look at that.
okay.
And maybe you can take a hand, Shipam.
Yeah, hi. Yeah, thank you for the very wonderful lecture. It was nice. So I have like maybe two follow-up questions. So first is like you use random forest, right? So the data is already labeled, right? The galaxy stars and quasars.
Yes, these labels, we assume is that the class star was a good classification, was a real trustable parameters for us to choose galaxies and stars. Okay, but this if we would be strict, if we were to write an article, then we should be more strict and get a spectroscopic data for the labels, so that we be very sure about being galaxies or stars. But for this notebook that we're interested in the explainability of the model, we assume that the class star parameter, we can properly separate galaxies and stars with that parameter.
Okay, so if I have like unlabeled data, then I will use unsupervised. So in that case, can I use this explainable AI to do the interpretation later? Like, is it applicable
For
when the
Yes,
data is
yes, you
like
can.
totally
The
unlabeled?
shop, yeah, you can use, yeah, you can. Shop, you can use it for supervised and unsupervised models. Doesn't matter.
Uh,
What you need to have are the descriptors. Descriptors in an unsupervised application are not the it's not the label, are not the labels,
yes,
there is no labels, but you can choose
yes.
this for shop application, can apply for anything you want. You just the shop values are related to properties that you can define, you know
Okay, okay, I see.
as I explained this morning. We can apply in morphological analysis. We can do that for the in the first order. We apply to know which descriptors are the best ones, or we can also apply SHAP for the hyperparameters of the neural network architecture. For the same
Okay,
problem, we have two applications from SHAP.
okay, I
Okay.
see. So, like, if I have like a time domain data, which I'm not sure what kind of objects I have, like it could be transient or planet or a star in that, or even an AGN or a quasar. So I have to use unsupervised, and then I can use this AI to do the interpretation later, right?
Yeah, you can use a SHAP, for example, for each epoch of trainment. You can use the percentage of right shoes, right. I mean the right result. When you get a right result, the percentage can be one input for SHAP, for example, in an unsupervised application.
Oh, okay. Yeah. Oh, okay. Yeah. I know. Yeah. Thank you. Thank you very much for the explanation.
Sure. Molebo, if you don't have any more questions, I'd like to show one thing that I promised in this morning, but I didn't show now in the afternoon. The bottleneck that we have to take care when you are using recurrent neural networks to time series prediction. May I?
Please go ahead.
Okay, so Just a moment. Okay, so I recommend you take a look in this Asimov Institute, where we have this is from the Netherlands, and we have the best set of different kinds of neural networks. This is a complete chart, you know, and we know that for recurrent neural network that has been applied for time series prediction, one of the most used one is the long short-term memory LSTM. So there are many papers published using that, okay? And this is based on this architecture. The goal of this architecture is to mimic the memory, okay? So you have here what we call the gates. And so what you see in this hidden, it's a recurrence in each neuron. If you see inside of each neuron, this recurrence means all those complex stuff that you see here. This is in Portuguese, I'm sorry. But the first gate here is a concatenation between the present and the past that we call memory modulation. Okay, that's the first one. And then we have this memorization or forgetting, forgetting some non-redundance in the time series, okay? And then there is a kind of gate to retain and to activate this value for the next step. So what's important here from the hyperparameters in the training work, for a given batch, a delta t that you are looking for, redundance to keep or not, for a given batch, if there is no redundance, it will be forget. You repeat that. That's a very important. This is the bottleneck in this use for stochastic process. For a given batch that is one of the hyperparameters, if there is no redundance, it has been forget. Okay, that's the most important thing in this LSTM architecture. Why? Let's take a look on that. We have forecasting for a very simple time series, just a binary one. We have 0 and we have 1, like a coin. So we have 0, 0, 1, 0, okay, 1, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1. Which will be the next? Someone can try. It's very easy because you can say 1 or 0. But anyway, our human mind is not able to say that very quickly, because it's a stochastic process. There is only probability related to the next value. But if you choose, for example, a batch, I'm sorry, there is no this E here, a leg batch like 4, okay? So we have a separating for like input here will be 0, 0, 1, output 0, okay? So you have 0, 0, 1, output 0. Then we have for this batch 4, let's take the next batch, 1, 1, 1, 1, right? So it corresponds to the second batch. The third one, you get 1, 0, okay, 1, and 0. That's the next batch. So the next one will be 1, okay, will be here. 1, 1, 0, 0. Okay, you to be the next. So
Once, One, sir.
You'll be 1, right?
Yes.
Yeah, that's the good answer. Why?
So, I mean, I compare these patterns in input. The first, suppose the input first column had 1, then output is 1.
Yeah, because the memory here, it's not a totally stochastic. There is some rule here. The rule is, doesn't matter what I put here in the second and the 30. The 40 will be exactly the first in each batch. Okay? So, for example, this one, doesn't matter this is 1 or 1, but is going to be 1 because the 40 in the batch will be like the first. This one, I have, doesn't matter, 0, 1 here. You have this equals to this. Here, same thing, same thing. So there is a deterministic memory here. So when I say LSTM, what LSTM is trying to figure out for 1,000 of epochs of a trainment. He's trying to get, and he's able to get this kind of repetition. And this, it works exactly when you have this kind of determinism here. Even it comes from a stochastic process, because it could be stochastic, it still could be stochastic. Okay, but of course, if I take a long time series for that, it will be not like this, of course. But for some reason, I can have some external influence or some deterministic source, and I can see there is some kind of memory for a given batch. Okay, so when we start to train and to find out this kind of repetition, we are facing the challenge to test all the batches. Batches equals to 1, 2, 3, 4, 5, 6, 7. So it takes time. Usually the people, they don't use like this. Sometimes they put a fixed batch, but they are not taking care about this value. They are taking care about the last value of the last batch. And when they do that, they simply repeat the last one. This is a very dangerous use of LSTM. There are many papers with wrong results, and it should be trained in the right way. Okay, this is also part of the XAI because I need to explain how I am choosing my hyperparameters, number of epochs, for example, and the size of batches. And I can put, of course, those two hyperparameter information in the chat if I want. So the output will be 0 and 1. Of course, there is a threshold to determine that in the neural networks. I can use all those libraries here. You can do that. But I can also do a very simple algorithm without LSTM, but that works as a LSTM. This program I program, and I'm going to send you that. I'm going to send you all the content that I showed this morning, this afternoon. Okay, I'll give that. I will share with you. Moleboge is going to share with you. And here, take a look in this program. There is no LSTM library, no keras, nothing. I'm just programming to do a searching of a such repetition for input data like this, okay? And I define a training set inputs as the array by this size of batch. So for this batch, there will be this first value for the value, this one, and this one, okay? And then I go to I create a neural network here, but it's just like a Hopfield one. That is a very simple one, actually. And I do some weights for the synaptic, and I see that after 1,000 epochs, if I run this program, I will find 10,000 runs, for example, interactions. I will find 0.98 or something like that. That goes to 1. Okay, so sometimes when I have a short data and a very simple domain, I don't need the LSTM. This kind of algorithm will be much more higher in performance than LSTM, for example. It's a very simple recurrent neural network without forgetting data, forgetting gates. You are just looking for repetitions. That's actually the way the LSTM was being improved. So uh, so that's the way you see the batch. Okay, that's the yellow values. What's the value here? So if I use the right batch, if I found this right batch, you realize that this value yellow is the same of the first in the batch for each batch. Okay, here. So and this one with this one. Oh, that's the secret. What's dangerous? Dangerous is when I have a stochastic time series like that. It's a real stochastic time series. So I took the orange for training. I use the green here to validate it. And I plot this and I say, oh, that's a very good prediction. But when I do a zoom here, I realize that it's not really a prediction. It's just plotting the last value one step forward. Did you see that? There are many papers published like this. And this is not prediction. Take care about that. So how I can prove that? Just doing cross correlation among both series. So I can get this cross correlation and I see exactly that in this time step, there is only a repetition from the cross validation correlation, you know? So that's a very important thing that I would like to teach you about LSTM. And I'm not going to details here, but of course, also it's a very important to choose the right activation function. There are many, you know that for LSTM, sigmoid and ReLU are very efficient for when I have some real memory in some internal batches. But anyway, this is also should be investigated in an XAI application when I go to interpretable analysis from the final result. Okay, so these are you skip. Let me. Okay, sorry. Okay, so I would like to finish my our lecture showing you the booklet. Booklet is almost done. I will share this booklet with all of you. Okay, so Bricks Astronomy Data Analytics Training Program. There are two booklets. The first one is Time Series Analysis for Physics and Astronomy, and the Module 2 XAI in Astronomy. So there are the booklet is almost done. Okay, it's a very complete one. And in a couple of days, we will finish and we send that for Moleboj, and Moleboj will send it for our students from this season of the BRICS data analytics course. Okay, that's it. Moleboj, please, you are in the floor.
Perfect. Thank you so much, Prof, and as well as Mariana. That was amazing. So I think we'll be looking forward to receiving the material from you so that we can share it with them as soon as possible. But from us, thank you so much. We really appreciate your time as well as expertise on this. And I'm not too sure if we're gonna meet next week, but I think we can communicate during the week about what's going to happen next week. But thank you so much, Prof, as well as Mariana. We really
Yes.
appreciate it.
For sure. Thank you very much, Molebo. And I would say that it's an honor to be here because we need to work very hard to bring BRICS countries together, especially human beings, actually, not only artificial intelligence. And so we want to be, I want to say that we need to keep in touch. Please send emails to us. We can do collaborations in many different levels. since undergraduate students, graduate students, R&D projects, innovation, and so on. So thank you very much again. Thank you, Mariana. Thank you, Moleboj, and thank you, all of you, because without you, there is no reason to be here. Thank you very much.
Yeah, it's a
Okay,
very nice course. Thank you.
no, perfect. And Prof, all the best with the game later on today. Hey?
Just a moment, I will